If your websites conduct transactions or collect sensitive data, you have a material risk on your hands that could cost millions. The client-side security gap is being exploited daily with attacks like digital skimming, credential harvesting, and form jacking. 98% of sites use first and third-party JavaScript to power and enhance the user experience, opening up the client side to the adversary. Unlike most things in security, there is an easy fix. Start by understanding your risk. Let Source Defense give you a site-wide risk report this week. Visit securityweekly.com/source defense. Every hack follows the same pattern. First, hackers exploit a human error, like a leaked key or a secret left in code. They gain a foothold and then pivot, moving from one compromised system to the next. Teleport breaks this cycle. Open source Teleport gives every engineer, every piece of hardware, every application an identity, replacing secrets like passwords and keys with auto-expiring identity-based certificates. Learn why most visionary businesses in the world choose Teleport at securityweekly.com/teleport.
Welcome back, everyone. Very excited for our interview today. Here with me from the Security Weekly team is Mr. Tyler Robinson, live from Black Hat, actually. Tyler, welcome.
Thanks, Paul. Surprisingly, we have decent internet for a minute, so hopefully that holds up.
Yes, looking very spiffy as well. With us today for this interview are Mickey and Jesse. And everyone's probably like, why aren't you saying their last names? Because they introduce themselves as Mickey and Jesse. So we're going to stick with that. Mickey and Jesse have presented several times at Black Hat and Defcon and several other security conferences, primarily on hardware and firmware security. For our audience, Mickey, if you want to introduce yourself.
I guess I'll introduce myself as a hacker, and I just break things and I make Jesse talk about them.
And Jesse's here with us. Jesse, how's it going?
I'm doing good. I'm Jesse. I break things also. I've been doing hardware security and low-level firmware stuff for a while, and it has some interesting things to find.
And I'm lucky to work with Mickey and Jesse at Eclypsium. Actually, I'll work together at Eclypsium. And so Mickey and Jesse get to get all of my wonderful questions all the time, asking about how these things work. And one of the lines of questions that I put them through is on secure boot. So I want to turn it over to Mickey and Jesse and give us a little background on secure boot. I mean, let's start with like why it was created and things like that.
Yeah, so historically, there have been a lot of issues with the security of the boot process. There have been things like boot viruses, other boot kits, things like that. Back in the legacy DOS days, even there were some that were like in 1984. So there's been a long history of attacks against the process. And when UEFI was created as a new boot mechanism, one of the things that they specifically tried to build into the process is this concept of secure boot in order to protect the boot process and the integrity and make sure that you're running the things that you think you're running on the system. So as part of that, they created secure boot. It's not intended for physical access attacks. So this is something that is primarily intended to protect against software attacks in general, where if you get somebody who gets code execution on the system, in a sense, the earlier something loads, the more privileged it is. So if you get code execution on the system and then use that access to modify and attack the boot process, it's a form of privilege escalation where you can modify the boot process and then modify the kernel as it's loading and do some really interesting attacks that way. So it is intended to essentially protect the boot process, protect the kernel as it's loading. So there's a whole mechanism for how it does that. And as part of that, there's basically there's a key hierarchy in the system where.
Well, hang on.
Sorry, go ahead.
I just wanted to, that's okay. I wanted to clarify for our audience, though, that because some people are like, well, I have secure boot, so therefore I have some physical protections, but it's not intended for that. Like the physical protection in this sense would be like your BIOS password. That's the mechanism to protect from a physical attack.
Yeah, one of the specific design goals of secure boot was to allow someone with physical presence to enable or disable secure boot or change some of the configuration. So it's specifically not intended, like secure boot itself is not intended to protect against physical access, but that is what you'd have like a BIOS password for. There are some additional things on some systems, like you might have a tamper detection if somebody opens the case on a server. Things like that are intended more against the physical access vectors.
And so now the pieces of the boot process that it protects is really interesting. Maybe you guys could run through like some of the pieces that are involved in the boot process and which pieces are protected and which ones aren't.
Yeah, so like we talk a little bit about just the boot process and how that works, where essentially you have firmware that's running in the system that, like when you buy a laptop or a desktop or server or whatever from the manufacturer, it comes with some code already built into the system. That's the firmware that allows it to start running. And while the system is booting up, it will start verifying the integrity of that firmware before it even gets to the bootloader. Some other things that happen in the boot process is the firmware that came with the system will load your operating system specific bootloader, and then that bootloader is responsible for loading the rest of the operating system. Like you'll have a Windows specific bootloader that will then load the NTOS kernel for Windows, and then that will start loading and running processes. It'll mount file systems and do things like that. But for the very first part, UEFI Secure Boot is starting to verify some components of the firmware. And then when it switches into what's called a boot device selection phase, that's when it determines where it's going to load the bootloader from, which bootloader it's going to load. So you can have multiple different operating systems installed on the same time, but you have a configuration that says, what is the first bootloader I'm going to try to load? So it'll do that boot device selection. It'll load the bootloader. It will do things like cryptographic signature verification and verify that the bootloader that you loaded, that the signature matches, it is signed by a certificate that your computer trusts. And then the bootloader will load the kernel, and it'll do a similar cryptographic verification of the kernel also, and then continue on that. It's called a chain of trust, where it's like you start out with the root of trust, and then each link along the chain needs to do the same verification to make sure that you're actually protecting the whole chain. So you'll start out with UEFI Secure Boot, verifying the bootloader verifies the kernel, and then the kernel will also verify things like loadable kernel modules. So
and that's
like a Windows driver also needs to be signed.
Oh, and so in Windows world, it'll go down to the driver level verification. Potentially.
Yes, Linux does this also. So like in Linux, you'll have what's called kernel lockdown is a recent thing of the last few years, where if UEFI Secure Boot is turned on, the Linux kernel will then turn on some additional flags to try and protect itself from attacks from the user, including enforcing driver signing verification, things like that. So you'll need to have signed drivers to load into your Linux kernel if Secure Boot is turned on.
So are all of the secure boots created equal? Are there different secure boot versions or enhancements leveraging things like TPMs or maybe enhanced TPM security? Where does that fall into and play into this?
Yeah, so primarily, like there's UEFI Secure Boot. So one thing that's pretty complicated about how you get the code that runs on your system in the first place is there's kind of a long supply chain for that BIOS initially, where back in the old days you had like legacy DOS, legacy BIOS, and then with the UEFI that essentially was created by Intel and contributed to what's called the UEFI forum. The UEFI forum then takes a specification. There's a group called Tiano Core that makes a reference implementation for that specification. And then that reference implementation has things like, here's how to do secure boot, including signature verification. There are things you can enable for doing what's called measured boot. So there's a distinction between verified boot, which is doing the signature verification, and then measured boot is taking the code that's running and then doing cryptographic measurement into the TPM, and then you can do policy decisions or other things based on those measurements. Like as an example, BitLocker uses those measurements in order to seal the encryption key for your drive into the TPM based on the status of those measurements. So if the measurement changes by the time you boot up and you want to unlock your drive, because the measurement has changed, the TPM will refuse to give you the key that you need to unlock to do your BitLocker drive encryption. So that's part of how the TPM and measured boot versus verified boot kind of interact. There are reference implementations of both of these types of things in the UEFI reference code. In addition to the reference code, that reference code is then taken by independent BIOS vendors, IBVs like AMI, Inside, Phoenix, who then add their own extra features on top of it, make their own changes, and then they sell that modified version to the OEMs, the device manufacturers like Dell, Lenovo, HP, Gigabyte, ASRock, Acer, everybody else. So there's a bunch of steps along the way that things can go wrong as well. But there is that reference implementation for just UEFI Secure Boot. You mentioned other implementations of Secure Boot in the PC ecosystem. Essentially, like if you get a laptop that you expect to run Windows, Linux, maybe some form of BSD or something else, maybe ESXi, those devices are essentially included as what's called the UEFI ecosystem, where Microsoft is managing the keys for that. They provide the keys that are used for this UEFI infrastructure. There are some other types of devices like enterprise routers or switches might have Secure Boot, but it's generally a different form than UEFI Secure Boot. So that's not specifically what we're talking about here, but there are other types of Secure Boot, and there are some hardware root of trusts also, where some manufacturers have added additional hardware to specifically verify things even outside of the UEFI Secure Boot process.
Yeah, I think it's a great segue
So
into
that long chain of trust there. Seems like there are a lot of places that could go horribly wrong, and it doesn't sound like if you're shipping some of that, someone like AMI sending that off to Dell's not verifying or validating the code. They're taking whatever AMI is giving them and just using it. So is that why a lot of these breaches of companies that manage things like code for Secure Boot, is that why those are so critical?
So there's the implementation itself, where maybe there's a bug in the reference code that then ends up in everybody. Maybe there's a bug only in AMI specific things, and then only OEMs that are derived from AMI are vulnerable to a particular thing. You kind of mentioned the overall supply chain in general. Microsoft controls there's what's called the UEFI third party certificate authority, and Microsoft has a separate production CA for Windows, and they basically have agreements with all the OEMs to provide their two keys as part of these systems, where you have the key that allows you to run Windows, and then this third-party UEFI certificate authority that then Microsoft signs all of these bootloaders for. As an example, if you want to run Ubuntu on your system, there's a canonical key that is used with the shim for Ubuntu, and Microsoft signs that bootloader. They don't sign Grub, but they sign what's called the shim. But there's a lot of other bootloaders for various different reasons that things have been signed using this key from Microsoft. So you mentioned kind of supply chain, and in a sense, because all of these systems trust the UEFI third-party certificate by default from Microsoft, all of the systems that are deployed out there will trust any of these bootloaders that have been signed by Microsoft. So if you have a vulnerability in these bootloaders, then you have an issue. We also don't know all of the different people who have had bootloaders signed. So we know like major ones like Canonical, Debian, but all the third-party vendors, we have no idea who has keys. Different vendors have different security maturity, so we're likely to find bugs in the code that's been signed.
So, Mickey and Jesse, if we could talk about the various, I mean, they're really variables, right, that can hold things. The primary platform key, key exchange key, the DB, and the DBX are those are like the four major components that help us implement this chain of trust, correct?
Yeah, that's right. So when you get the system from the manufacturer, let's say you open up your laptop, take off the case. There's going to be a SPI flash chip on the motherboard that contains. This is where the firmware is stored in the first place. This is the code that runs when the processor starts booting. It has this firmware. It also has a region of that SPI flash that contains what's called UEFI variables, which are essentially configuration data for the system, and they have different attributes. But a number of these variables are provisioned by the OEM, like Dell or Lenovo would have their platform key provisioned into the system. So you'd have like a Dell platform key for that specific system. And then there's also the key exchange key. And then the key exchange key will usually contain a OEM specific key. And then it will also contain a Microsoft key exchange key. And there's a little bit of a hierarchy there where in order to make updates to the key exchange key, you need to have a request that's signed by the platform key. There's also DB and DBX, which are essentially, you could think of it as like an allow list or a deny list for the code that's running on the system for that signature verification process. So if the system is trying to load a bootloader and it looks and checks to see, is the signature valid? Is it signed by a certificate that was in the DB allow list? Mm-hmm. It would generally say, yeah, it can run. But if it is also in the DB or the DBX, sorry, the deny list, the deny list overrides anything that's in the allow list. It's essentially like a revocation list. So DB is where things start out. And then if you need to revoke something for any reason, you'd add entries to DBX or the deny list, where maybe there's only a single bootloader that had a vulnerability, like the Kaspersky rescue disk that we had a few years ago. There were a few updates that needed to be made to DBX to block the Kaspersky rescue disk bootloaders. There was a vulnerability a couple years ago. That's a relatively easy one where it's only a few entries. If you have a vulnerability like the Boothole vulnerability, which was basically every version of Grub from 2010 onward was vulnerable and had bugs in it, and you need to revoke all of those, that's a lot more difficult, because if you're revoking every individual signed bootloader by hash, that's more difficult.
But wait now. If I have a bootloader, right? It's Paul's bootloader. Yeah. Wouldn't I have to submit that to Microsoft? And
yes.
Do they do some kind of code review on that to go, yeah, like it's good, we'll sign your bootloader, Paul?
There's some review. I don't know how extensive it is. A lot of it is along the lines of, is this what we think is a legitimate organization? There are some questions asked about things like, how are you managing the key that you're signing things with? Or are you using like a hardware HSM or something like that, where it's mostly like, what are the compliance steps that you're taking to control access to this key? I don't know that there's in-depth or sufficient review of the code itself to verify that there's any or not issues with it, because there have been some pretty obvious vulnerabilities found. So I don't think
like
that there's historically been anything sufficient to actually find these types of bugs. So I believe the review process is mostly just compliance issues.
And it's Mickey and Jesse's job to find vulnerabilities in the bootloaders so that we can update our revocation list.
Basically,
among other things.
But yeah, so vendors will make a request to Microsoft to have their bootloader signed, and then fill out a form and some questions, and if that's approved, Microsoft will sign their bootloader for them.
And that means that the hash of that gets in the DB.
So no, the DB will have a hash of the certificate that is used to sign the bootloader, not the hash of the bootloader itself. So the DB is the allow list. It basically has a small list of certificates, and then anything that is signed by those certificates is allowed, unless it's also in DBX. And DBX can either have individual hashes to revoke specific bootloaders, or you could put an entire certificate in DBX to revoke everything that has been signed by this certificate. And there have been a couple cases like the Boothole issue. There was a canonical intermediate certificate authority that they were able to put into the DBX to revoke everything that had been signed by that, instead of having to add 1,000 or 500 different individual hashes.
And it's still 32 kilobytes of size limitation that we have on the DBX?
It depends on the system. So there's some systems that can have up to 64K. One of the big issues that we run into with updates to DBX is that it's not done very often. So it's not a code path that is exercised by OEMs very often. So a lot of times when that Kaspersky update came out, we had hangs, and the system, systems wouldn't boot or wouldn't take the update. Microsoft pulled the update. Microsoft tried to put it out through Windows Update, and then pulled the update with less than a week later because systems were failing. So it's not code that's exercised often. There's also cases where you could just run out of room in that space for the DBX list. There were some cloud environments where they had enabled secure boot in your virtualized environment, but there wasn't room for the complete DBX update list, even for the Boothole vulnerabilities that we had a couple of years ago. And the cloud systems just physically couldn't take the update until you reconfigured it, changed the settings you were using, and ported. So there was a setting that you could use as basically a small space for these variables, or a larger space for the variables, but the data store backing it was not compatible. So rather than just flipping a switch, you needed to physically read all the variables from the old format and port that to the new format. So even in a cloud environment where you didn't have the physical storage just in a SPI region, we were still having issues with just the size of the revocation list. So there have been some efforts to try and optimize the way that you can add additional revocation. So revocation is definitely a difficult problem with secure boot, and there are some if we have lots of more issues like this, we definitely will run out of more space more quickly.
Right. Mickey said in the beginning that he lets Jesse do the hard explaining of a lot of stuff. Mickey, I want to go to you and pose the question of, so you've uncovered new vulnerabilities in bootloaders. Is that the focus of the Defcon talk?
Yes, we found 3 new bootloaders. Well, I say 3, I mean 3 vendor created or supplied bootloaders. We don't know exactly how many versions of each bootloader were signed by Microsoft, because Microsoft tends to not share that information. But we do have 3 unique ones separated into 2 groups. One group is a bypass using a UEFI shell, which is, as it sounds, it's a shell that you can boot into from a UEFI environment and run commands, and it has built-in commands. And the other group is just a simple bootloader that loads and executes unsigned code. We call it the we don't really have a name for it, but we came up with nicknames so the mother of all bootloaders or any booter or what. It's just the one type of bootloader that whatever file you give it, EFI file, it will just run.
It'll just boot it. So it's missing the check. Yeah, it's missing the checks to verify the signatures for any code that it runs.
Yeah, it doesn't use the built-in mechanism to load and run an executable that it enforces the checks. It just loads it and runs it in its own manual way.
That seems very handy from an adversary standpoint.
So technically speaking, the old Kaspersky Rescue Disk did the same through Grub, but it was a dance between around 4 binaries, and you have the whole Grub environment. This thing is just one file that's under 100 kilobytes.
Oh, so hence the name of the talk, one bootloader to rule them all.
Yep.
Now, the other group that you mentioned, Mickey, was the EFI shell. Is that doesn't require physical access? That shell can be accessed programmatically?
So EFI, the only difference between the two types of bypass is the first one that I mentioned that loads whatever file. It can be done in a more stealthy manner. So you would, as an attacker, you would just switch the bootloader and the disk, and you won't see any indication on the screen. But with the shell, because of the way the shell is, it shows a shell screen on the display that gives you the ability to type in the keyboard physically if you're at the system. However, that shell has a built-in automation mechanism that if you don't type in anything for 5 seconds, it will execute a script with a predefined script file name that's stored in the same location. So you could technically automate it if you do it on a system that has no one near its screen or it doesn't have a monitor.
That also poses risk to things like IPMI or out-of-band management, even without the keyboard or the physical access too.
Systems that are not monitored,
nobody's going to be sitting in a server. If you have all your servers in the rack, like nobody's going to have a display hooked up to those. So that's pretty useful. Also, if you just reboot it in the middle of the night when somebody's not looking at their laptop, it's still totally useful then too.
So then,
that's terrifyingly awesome.
how do we remediate, or I guess first, how do we monitor for that? Like, how do you know if your bootloader's changed?
So there's several ways to do this. There's you can monitor the files in the EFI system partition that hold the bootloader. You can monitor the environment that can be modified that you can see from runtime. If there are any hooks that are inserted into any EFI services that are available at runtime. What else? I guess there's not a lot of visibility from the OS to whatever the firmware was running. But self-integrity, I forgot to mention, there's also the BitLocker, the whole TPM measurements that when you measure, you have a measurement system that you can measure all the execution of binaries and hashes of things during the trust chain. So if you have BitLocker enabled or TPM enabled and supported, you can monitor the execution, and if some unauthorized execution happens, you will see a change in the TPM PCR hashes, or the system with BitLocker initiate BitLocker recovery.
Yeah, so BitLocker recovery will come into play if things change in a way that's not expected and the attacker hasn't done something like suspend BitLocker temporarily while they're doing the attack. So there are things that would cause BitLocker recovery. You can, as an attacker, do some of these things to, even if BitLocker is running, make it so that the TPM measurements are what Windows expects. So it might make sense to monitor the TPM measurements just on your own, and not depend on Windows alerting you if something is wrong.
Yeah, because I saw
this
commands
merits.
that Microsoft had that were like, here's how you disable BitLocker for one reboot cycle.
Yeah,
That's exactly what the attacker can do. Is like they can just disable BitLocker or suspend BitLocker, and then have their own attack measured essentially.
Yeah, if you look at the knowledge base that Microsoft released in the update, you can see that there are two ways to do this if BitLocker is enabled. If you don't have device guard enabled, you do only a suspension for one reboot cycle. And if you do have device guard enabled, you do a suspension of BitLocker for 3 reboot cycles. And then also, if the attacker has an admin on the system, they can suspend BitLocker all the time. If they change the BitLocker, so they can change the bootloader and then update BitLocker every time as they want.
Right.
Unless you monitor that or attest to it in the backend.
Then you run into the fun case of if somebody tries to remove your malicious bootloader, then they go into BitLocker recovery, because then your malicious measurements are what's locked into the BitLocker configuration at that point.
But so that's BitLocker, right? But the modifying of the DBX is a different. So then attackers can't modify the DBX because of the certificate chaining we talked about earlier, right?
Right. So if you have physical access, all bets are off, because then you can modify it that way. But through software means, I mentioned that there are some attributes for these UEFI variables, and some of those are things like you need to have an authenticated request in order to change the. You need to have an authenticated request in order to change the value of certain variables, and for those, then you need a request that's signed by the hierarchy and the key hierarchy. So in order to update DB or DBX, you need to have a request that's signed by the key exchange key. So
those,
So we
those are what's called the authenticated variables.
Yes, authenticated variables. So we mentioned a little bit about the revocation list. So those are signed by Microsoft. So there is this DBX update that is published, and that request is signed by Microsoft also in order to apply those updates for the revocation list.
Right. So what's coming down that people need to be aware of for remediation is an updated DBX that has to be applied to all of your systems, and that has to be signed by a valid signing authority such as Microsoft in order to be applied to your system.
Right. Yeah. So Microsoft has.
I was going to say, then you have to pray that. I'm sorry, the delay is awful. Then you have to pray that your firmware doesn't have anything that will make it break after the update.
Right. Like if you break the secure boot chain and you forget your BIOS password, you can't go into your BIOS and disable secure boot, and you've just locked yourself out of the system.
In some cases, there was I think there was a bug at some point in some versions of firmware where if the space was running out and the firmware was trying to reclaim it, it would trigger a bug in the reclamation process, and then it would completely hold. And that was an unrecoverable issue.
Oh, I see. Yeah, well, because if you corrupt regions of your SPI flash, all bets are off.
Yeah, definitely. I mean, I would definitely recommend to make sure that you know your BIOS password before you manually do the update. That Microsoft has released updates for Windows systems, and it looks like those are being pushed out through Windows Update. There are a number of manual update packages if people want to update the system themselves. There will need to be a DBX update provided for other systems. One interesting thing with the way the UEFI ecosystem works is that, let's say I don't even run Windows on my system. If I have a Linux system, and that's the Linux system is using the Microsoft UEFI third-party certificate in order to provide UEFI secure boot, even though I'm booting into Grub and booting Linux, someone like an attacker could potentially bring a vulnerable bootloader with them and then use that in an attack against my system, and then once they've done something to modify the system, they can then chain load Linux and boot into Linux and then modify the Linux kernel as it's loading as well. So just because you are not running Windows doesn't mean that you're not affected by these issues.
Right. But if a user updates their DBX and they're running one of these bootloaders that are vulnerable and has been put into the DBX, your system's not going to boot, correct?
Your operating system will not boot, but you can still interact with the firmware because that's still runs. So there is a workaround for that. Mm-hmm. Every modern system has DBX and it has DBX defaults. So in some cases, even after the update, you should be able to go into BIOS and revert the DBX to the defaults prior to the update.
So there's a
as long as you know your BIOS password.
Right.
As long as you know your BIOS password, and
you can also generally turn off secure boot temporarily. So that's another way that you can get the system to boot up if it fails to boot afterwards. So if you know your BIOS password, you can go in, you can turn off secure boot, then you can boot up, do whatever. In this case, these are third-party tools. There's like a rescue disk, things like that. So you can update your system and make sure that you have the latest version of that bootloader that you're using, and then re-enable secure boot.
Right. So Microsoft has to sign the updated revocation list. Users and potentially OEMs have to make sure that up gets pushed out, but also the software folks that make the bootloaders have to, well, not just update their code, but get another, go through the signing process with Microsoft again to remediate the issue.
Yes. Yeah, exactly. So they need to get a new version of the bootloader, submit that to Microsoft, get it signed, provide an update to their customers. The customers can then deploy that on their systems. And then after that, they should update DBX. Is kind of, there's a whole series of dependencies of order that you want to do things in if you're actually using these tools.
And all this happens seamlessly, right? This is
that's what I'm going to say. So this isn't going to happen for a while.
Yeah, there's a lot of steps in this supply chain that, I mean, ultimately put people at risk.
Yeah. Yeah, we basically are trusting everybody to not screw up their bootloaders.
Yeah, and that's, it begs the general discussion point of who's responsible for, one, finding things that should be revoked, right? Finding something that carries a signature that needs to be revoked, who's then pushing out the updated, signature or verification, and then who's applying that, verification. And that gets into muddy waters and kind of scary, who's maintaining this series, this chain of trust for our systems, for not just bootloaders, right, but all of the code responsible for secure boot, but this extends in your operating system to things like, apt, get, update, and upgrade. Those are signed as well. It's the same kind of philosophical issue, if you will.
Well, yeah. Do you mean theoretically or de facto? Because
I guess both.
De facto, I would say Microsoft all the way, because they first, they have the money, they have the manpower or human power. They control most of the ecosystem that uses secure boot, and they basically took responsibility over it since they volunteered to maintain the chain. But that said, they also architect their new operating systems to avoid trusting the firmware. So they're like, I'm okay with maintaining this, but I'm not going to trust that chain, and I'm going to try to evaluate everything and not trust the firmware that I'm running on.
Right, because Microsoft builds that chain of trust into their operating system and pushes these updates out through Windows updates. Like running Windows, you should theoretically, practically, right, you should get these updates from Microsoft to update the DBX, to update your firmware. I mean, especially if you're their brand of hardware.
Well, speaking of that, the two facets that I just mentioned, there's a third facet to this, which is the Microsoft own vertical and their own Surface product line that has their own firmware version, their own bootloader. They have their own CA that's just Microsoft for their own bootloader. So very similar to Apple, they have the whole vertical control for the trust chain.
So is Microsoft and Apple in a better position security-wise to keep these things up to date and keep people more secure?
It's a yes question mark, because they do keep people more secure. For example, these bootloaders that we found would not run out of the box on a Surface laptop, even though it's running Windows and it's assigned by Microsoft, because Microsoft has a more restrictive list of bootloaders that they allow to run in that product line. Same for Apple. Apple has their own, but it's a very small subset that they allow for the specific product and the specific family of products. Anyone else who runs any other piece of hardware, like I understand Surfaces are good for some people, for some use cases, for some business needs, but engineering laptops, or like your engineers in your business, they won't use Surfaces most likely. They will use more beefier hardware, more enterprise class third-party OEMs like Dell. Some use gaming systems as engineering platforms that has even less security. So it is kind of more secure, but it's not as prevalent.
Yeah, and that's one of the things I've learned working at Eclypsium is as you work your way, I don't want to say down, but like away from the enterprise branded in hardware and software that's really made for the enterprise, this stuff gets like even wonkier. In updates are less frequent, and it's difficult to determine whose responsibility is it to update firmware or revocation list on your hardware devices, right? Because you've got you talked about in the beginning, you've got your operating system, you've got, your firmware, your OEM, two different hardware OEMs, right? You've got Dell, and Dell may buy the hardware from AMI, and then like who's responsible for getting all those updates out?
Oh, and it gets worse. Because let's say you buy a laptop, you use it for 2 years, or you buy a computer, you use it for 2 years.
My MSI laptop?
Yeah, for like you use it, and after 4 years, it's still a valid piece of hardware. But do firmware updates keep being released? Like you have systems, industrial systems are designed to be run 5-10 years, like without interruption. Their firmware updates are rare, and you barely see those. And I don't know how far back. What's the official number for a support timeline for a specific platform from an OEM? Like Dell says, for Latitudes, we support them from a firmware perspective 5 years back, or 6 years, or 10 years. I don't know. There's no official number.
Yeah, I noticed that with my MSI laptop. It was like after 2 years, they stopped making any firmware updates for it. Am I going to get a new one? I don't know.
Yeah.
Then you look at some of the cloud providers and the hypervisor layer and the hardware that's running on. The update process for some of those, like you're talking about hypervisors on hypervisors and multi-tenant clients, like no one's updating those at mass scale immediately. It's going to be a while before those get it. So like some of the vulnerabilities that you guys are talking about have nation state implications. So how do we begin to start to secure and even just evaluate what the risk posture we're taking on, because we're not able to update some of the firmware, or some of our stuff is running on something that we don't control, and that firmware doesn't get updated, but we don't even know.
One of the questions I always have along these lines is, can the open source community kind of pick up support? And I know the Core Boot project is gaining a lot of momentum. Is that feasible to put open source code on your system? I would imagine that on certain hardware that might be difficult, right? And the second part of that is like, could open source actually help in this sense to have better support for longer periods of time on this particular firmware?
Yeah, there have been some efforts to essentially make open firmware for different systems and have like a replacement firmware. One issue that we run into. So I mentioned the reference code Tiano Core. That is open source code, but you generally can't take just the Tiano Core code, build that, and then flash that to your like Dell laptop or whatever. There's generally some open source components that go in for the core, but then there's also some closed source OEM specific things that happen. So I know there's a few projects to have different laptops that are more open source mindset, where as much as possible is fully available and fully published. I think it's not a bad idea, but there are some issues that you run into if you try to do that with modern consumer hardware devices. There might be a push to have that more possible in the future, but currently you can't generally just build your own BIOS and then flash it to your Dell or Lenovo or HP laptop.
Yeah,
that's
like
the
today
technical
it has to be
difficulty.
supported. Go ahead, Mickey.
That's the technical difficulty of things where we talk about the open source community. I want to mention a couple of other things with open source firmware and open source in general that we've seen with our experience with Grub. In some cases, so there's a lot of great things coming out of the open source community. Like, aside from Core Boot, there's Heads, there's all the Trammell research and Trammell Hudson, and others that I'm probably forgetting to mention. But the problem with that is some of these are either motivated by individuals or underfunded in large corporations, or are running as a volunteering effort. That's the downside of open source. When you have a business that's backing it up, like Google and Core Boot, that's aside, but other things that involve open source firmware, from my experience, it's been tough.
Yeah, for a lot of reasons, right, Mickey? The developers either, like you said, are underfunded, so they're not getting paid to maintain this code. They lose interest, they get new jobs or what have you. There's a lot of reasons why your laptop might be supported, that firmware would be supported with Core Boot, but then, people are like, I don't feel like updating that anymore. Right?
You see a lot of problems when you have someone with a lot of motivation that wants to contribute, that wants to spend a big chunk of their life and sanity into making everyone else secure and better, but then they hit the bureaucratic wall where you have specific NDAs for specific manufacturers that you need to write the firmware to bring up, but you can't open source because of licensing agreements. And that's for each vendor, for each piece of hardware, for the platform that's designed by an OEM in a certain way. Yeah, so you'd rather go find another job.
Right, and there's not just you, EFI. I mean, you guys did a great presentation that I was watching from 2015 in Paris about all the different components. And we have a lot of resources like that at Eclypsium, right? But when you look at just UEFI, it's one firmware component or subsystem in your computer. There's how many different, in a modern computer today, how many different CPUs and different firmwares are running? Is it over a dozen at least?
At least. Let's see, modern. We can start listing them. So like the USB controllers, the PCI controllers, PCI bridges, the ME or PSP, the graphics cards, graphics controllers, any external, any EC that you have on a platform.
Right.
What else? Audio. Some audios have them. Power control, battery control. Not all of them, but some of them have integrated logic and firmware that you need to update. Charlie Miller did a talk a while back about batteries and Apple laptops a while back. It was the TI BQ controllers. They had passwords
your
written
EC
in a data sheet.
Yeah, because your EC firmware controls your battery, but your battery also has firmware that runs on it as well.
Everything has firmware at this point. Almost everything.
Yeah, webcams, network controllers, cellular modems, all of those things.
Forgot about those. Yeah, we had a talk where we took a cellular modem that was plugged in internally via USB lines and had it emulate the keyboard and have that key press and get into BIOS and change things. And then
so
webcam.
Yeah, it was essentially a complete Linux distribution running inside of an M2 card that you just plug into your laptop or tablet, and it was a complete separate computer. And it's common for any sort of non-trivial device like that to have firmware.
I think it's a great segue to talk briefly about the Linux vendor firmware service as an attempt. I think it's Richard Hughes, right, that runs that project. But this is where vendors have to participate to provide firmware updates to this project, open source project. And then Linux users can then start using this service and this project to apply firmware updates to all of these different components. But this all hinges upon the first part, where manufacturers have to provide those updates to this project.
Yeah, definitely. I mean, I think it's a great project, and it has a lot of theoretical good things coming out of it. But as an example, I have an Asus desktop that if I run LVFS, there's like a firmware update tool, and I check what devices I have available firmware, and it detects like 4 different devices. None of them have firmware update, including it can't do a DBX update or UEFI firmware update for me, even though it's a relatively common system. So there's like my SSD firmware it detects. There's an update for, but it doesn't have the ability to actually give me that update. So it does require the vendors to cooperate. And I kind of like some of what Richard has been doing to make it more obvious which vendors have been better about cooperating and having dashboards and stuff like that to kind of name and shame the vendors that are not good at providing updates.
So for just to round it out and for people to like what you want them to walk away with from this interview and from your talk, what should users be doing to protect themselves?
I mean, I think just knowing that you have code that's in the EFI system partition that Mickey mentioned, like monitor for changes there, make sure your DBX is updated. There are manual tools, like if you're running Windows, there's PowerShell tools you can use to check the contents of your DB and DBX, your platform key exchange key. If you're using Linux, there's a DBX tool and other things you could do to manually check the status of that as well. Just knowing that these are updated or that these are updatable and should be updated is important. Knowing that you have the bootloaders to check in the EFI system partition, understanding just the idea of like one thing that we talk about in computing and security is the concept of like a trusted computing base. It's like, what are all the things that affect the security implications of my environment? And in some sense, all of the bootloaders that Microsoft has signed are in the TCB for your system, even if you're not using those bootloaders. And that's a big supply chain thing to think about as well, just because there's all these different vendors that have varying different levels of security maturity. Some of them have probably had security issues in the past, and they're like, well, we don't want to do that again, so we'll actually do some checks ahead of time. And other vendors are like, they don't know what they're doing, and they focus on some third-party tool and try and work on that, but they don't focus on the security aspect of it. So we're going to run into more issues like this. It's just something to be aware of, something to watch out for, understand the types of threats to look for, know the order of how to remediate this is all important things to understand. Anything else, Mickey?
Yeah.
Well, I'd say update. And if you're an IT professional or administrator, do an update on a small batch of devices, a small sample set of all, something that represents the ecosystem in your organization, so you can catch any potential breaking issues beforehand before deploying it to the environment.
Awesome. Mickey, Jesse, thank you so much for appearing on Paul Security Weekly.
Thank you for having us.
Thanks. This is fun.
With that, we'll conclude the show. Thanks everyone for listening and watching. Over and out.